Okay, I'm resuming session number 13 of the mathematical signal processing course. And I just would like to remind you that we are going to do mathematics which is relevant for signal processing. So what you see here is some spectrogram of whistling that I just did 2 minutes ago. And it is just a recording of the change of frequencies as a function of time. So I will activate this program, this STX program of the Acoustic Research Institute of the Austrian Academy of Science, and you will see the spectrogram of my voice recorded by the same microphone that's recording the talk. So you will see my voice, and depending how I raise my voice or whether I do whistling, you will see some pictures. Now, if you would ask yourself, is what we are doing in mathematics, computing Fourier transform for fancy functions, is that helpful for what we are doing here? And the answer, unfortunately, is no, it's not really relevant in the strict sense, because what we are showing here is, well, something like a Fourier transform of something that you cannot write down in a pointwise sense. It's something that we have recorded or that we are recording online. And so I would say the theory that I'm going to prepare for you is a theory of things that can be measured, which are allowed to produce spectrograms. And hopefully these spectrograms are bounded functions of two variables. And that's much more interesting than having pointwise almost everywhere recovery of the function under very restrictive assumption of integrability. We'll see, for example, we cannot yet recover at the moment the boxcar function from the sinc function, because the sinc function is a bad guy, it's not integrable. And clearly you will have definitely problems to recover the boxcar function at the jump points, because if you give me either the boxcar function with open ends, so indicator function of open interval -1/2 +1/2, or you're giving me for the closed interval, all the integrals will be the same, so you never can recover it. I mean, fair symmetric methods will recover the midpoint of the jump, so it's the value 1/2 at the side points, but that's not really relevant, because I think computing pointwise values of Fourier transform is not so relevant. So what is the idea of these spectrograms? You're saying, I'm getting 44,100 samples per second, for example. This is the sampling rate that you see in the left lower corner here even. And then you take FFTs, fast discrete Fourier transform of these sampled versions. I mean, we pretend it's samples, but actually it's averages. It's like taking a picture, a photograph, it's not counting photons, but it's integrating over photon intensity. So it's a local average, but it's so small that you can think of it as a sampling value, because things are not changing kind of chaotically too much. So a spectrogram is something that you get by doing a sliding window Fourier transform. So you localize things and you're cutting it into functions, into pieces. Now, even if you look at this program you see here, you can change the window lengths. Here in the program, it's 100 milliseconds, which means 1/10 of a second. That means, roughly speaking, the FFT which is employed is something which deals with 4,400, which is about 2 to the 12, 4 times 1024 would be a pure power of 2. And then this is done, but with overlapping intervals. Now, I would say this is a very concrete form of something like a BUPU, where this is the size of the thing, and this is the overlap that you have. Here, for displaying the picture, we don't need to have a partition of unity property, we just cover everything. But that's kind of a motivation for us to go, instead of infinitely long signals with an infinitely fine spectrogram, we will go into a situation where we are computing local pieces and do it in this way. So going back from applications to the mathematical background, so you have an orientation, hopefully a little bit. I was showing you just at the end of the last session that by this particular choice in the fundamental relationship, we wanted to have the G such that we get G hat bar. We insert into this relationship, and then we get that the Fourier transform of the scalar product of two Fourier transforms is the same as the scalar product of two original functions. And that gives us the isometric property. Well, but the isometric property is only valid for a dense subspace of L2, and that's why we need to work a little bit, but I think this is not worthwhile to be discussed in too much detail, how to extend it. So we assume that L2 is the completion in a sense that has to be discussed of the L2 of the space of Fourier invariant of the Fourier invariant space of L1 functions which are in the Fourier algebra, and we extend it to what is called a unitary automorphism of L2 of Rd. Now there are two vocabularies that you might not be completely familiar. Let me recall, a unitary matrix is a matrix where the inverse matrix is the same as the transpose conjugate. But the other way to express it, if you have a unitary mapping from Cn to Cn, it's a mapping which is a change of basis from one orthonormal basis to another orthonormal basis, or equivalently, a bijective mapping from Cn to Cn, which is preserving scalar products. And that's the property that we are having here. A unitary mapping on the L2 space, which is a space of, I would say, a little bit more general than measures of bounded measures. It's a space of mild distributions, we will say later on, which has a scalar product structure and a norm. And if a mapping is preserving this scalar product, so you can do the F and G, or you can move it over to the Fourier transform domain, and this is preserved. So that's why it's called a unitary mapping. You have to work a little bit first to extend the given mapping from the dense subspace to all of L2. And then, of course, you have to show that it's still surjective. So that means it's not only going from one space to another, like an embedding, where you would say, I don't know, you put the plane into 3D spaces by putting xy into the xy plane, which means x comma y is put into x comma y comma 0. That's exactly, of course, preserving lengths, angles, scalar products, but it's not surjective. So if you want to claim that's bijective, you have to work a little bit. But of course, we have seen L1 intersected FL1 is invariant. So it's in the target space, and it's so big that you can easily get any L2 function on the Fourier transform side in the same way. So if you're asking me, well, how can I get a given element in L2, like, I don't know, the sinc function? Well, approximate the sinc function by functions which are in this space. That could be a finite linear combination of triangular functions, a truncated sinc function, a little bit interpolated with piecewise linear mapping. They would be Fourier transform of something, and then you take limits, and because of this isometric property, you can extend it. Now, a unitary isomorphism or an isometric mapping from one space to another, if target space and original space are the same, you would call it an automorphism. Auto in the sense of map self-mapping. So that's the complete statement. So the Plancherels theorem says we have engineers say energy preserving statement. The L2 norm squared, it's the integral over F absolute squared, can be viewed as a time concentration of the energy or a frequency concentration, and they're equal. Now, there are many applications, and maybe I'm telling you that two functions, let's assume band limited, meaning nice functions which have a Fourier transform which is living in some interval, they will be orthogonal if they are living in different frequency bands. So if you're asking me what is F with G, the scalar product, And I'm saying use Plancherel to go to the Fourier transform side. Now, if two bump functions live in different frequency bands, their product in the integration according to S, of course, should be the corrected, will be 0. And that's the reasoning behind digital audio or radio transmission. You're receiving signals at different frequency bands, and you can separate them. They're not too much mingled. You can filter out them because they are living in orthogonal subspaces. So if somebody is giving you a vector in R3, it's no problem to determine the X, Y, and Z coordinates, and that's exactly what you can do using this orthogonality. Now, I was playing around and I was planning originally to introduce to you first the Wiener algebra, then take, which is a subspace of L1, a more decent subspace of L1, then take the space of the Wiener algebra intersected with its Fourier transform, and finally introduce the round object, which I have already shown to you, this nice small object, which is called the Siegel algebra S0, and some people call it Feichtinger algebra. But then I realized we can do it all at once. That means I will do now a quite abstract step again, which is not in the books. So Riemann-Lebesgue and Plancherel are in the books, with slightly different arguments, but especially the last step of Plancherel is quite traditional. But what's coming now is kind of completely based on the material that I have developed so far. So we go into an abstract setting, and that looks like a little bit an overkill in terms of terminology, but you will see it's quite useful to have it done in an abstract way first, and then apply it to different situations. So I will use this kind of private notation. It's kind of private notation of a homogeneous Banach algebra of functions. So I'm thinking of the Fourier algebra as something which is a Banach algebra with respect to multiplication, but it also has this nice property of being translation invariant and having a continuous shift. So going through the properties, and I will do it a little bit slower now, I'm trying to say what is the scenario that we will work. I will think of the Fourier algebra inside C0 by Riemann-Lebesgue, but we can do it more generally, and of course you can choose A equals C0. That will be one of the examples that we will use. First assumption, the compactly supported functions are dense in the algebra, in the sense of the norm, and the algebra itself is dense in C0. The second thing is, and that's why it's called homogeneous space, translation is isometric and it's continuous. So small shift parameters give small deviation in this norm. For every element, the limit is 0. In the applications, we will also have bounded approximate units. So it's something like plateau functions, which are acting more and more like identity operators when applied to a given element. And we are allowed to make regular bupus, which means we can take a function in this algebra, and because of the property number 2, all the shifted versions, so all these psi of x minus k, which are tk shifts of this, they all have the same norm. So we get a bounded family of shifted functions which add up to constant 1. And I would say, let's assume that this guy has compact support. Now, I will use the property on 202 and 9, which is saying that L1 is convolving on A by in the corresponding mapping with the corresponding estimate, either by verifying it in a concrete way, as we will do it in our examples, or by arguing later on that you can derive it automatically from 2 and 3. So you recall that shift operators are convolution with the Dirac delta. So you know, of course, that 2 plus 3 give you that, well, it's a 2 gives you that you can convolve with discrete bounded measures. And the continuity of translation is useful to allow you to do the transition from deep psi mu to mu itself. So 2 and 3 give this, but I don't want to do it, prove it in an abstract way, because in our cases, this property will pop up for free. So of course, I was already indicating that the Fourier algebra, which is a Banach space with the transport of norm, is such a Banach space with this property or so. So I've tried to give you an indication of the argument, and maybe we don't have to do all the details. For example, here I'm writing that we can use the sinc square function, which is one of those nice functions, as an approximate unit for convolution. So if you take this and apply the S0 operator, you will have an approximate identity for the convolution algebra L1. But the Fourier transform of this is the delta. So that means if you take an element in the Fourier algebra and you stretch it more and more, multiply it with a very far stretched function of triangular type, you're getting a compactly supported function, and that will be convergent. Actually, I've shown you graphically that if you don't take the convolution of a boxcar by itself, but of a big rectangular with a small rectangular, you will get a trapezoidal function. So I find multiplying a function in the Fourier algebra with a stretched trapezoidal function quite nice. So assume the trapezoid, the original trapezoid is going from, has a plateau from -1 to +1, and it's starting at -2 going to +2. And then you stretch it by a factor of 100, so you choose a rho equals 1 over 100. You get a huge plateau from -100 to +100, but also a compact support between -200 and 200. So this is the one-dimensional situation, and I just indicate here in 2D and higher, you take products. You take sinc squared of x times sinc squared of y and so on, and do the same stuff here. So this is giving you that the compactly supported elements in the Fourier algebra are dense, which is the same as to say in L1 the band-limited functions are dense. Maybe a warning. We have seen by definition the compactly supported functions are dense in L1. Now we hear that the band-limited functions, so the functions with compactly supported Fourier transform, are dense. So why not work with the space of functions which are compactly supported and have a compactly supported Fourier transform? That would save us a lot of approximation and so on. Now, actually, I'm always telling this story. During my thesis, I was thinking this is a nice space and it will be dense in L1, for example. But no, this is not true. The Fourier transform of a function with compact support is an analytic function. And that means it has a power series expansion. So if that is 0 on a whole interval, so if it has compact support, it would have this property, then it will be 0 everywhere. So it's only the 0 function which has compact support on time and frequency side. So really we have to always move between compact support approximation on the time or on the frequency side. But again, the first point in our estimate is true. So we have, just recall, the density of compactly supported functions in the Fourier algebra, and of course the Fourier algebra contains L1 intersected FL1, which is allowing us to do piecewise triangular functions, which is good enough to approximate C0. Now I would like to discuss points number 2 and 3 for the Fourier algebra next. What is translation in the Fourier algebra? And we know that modulation is a frequency shift. So we have to see, well, is this a Fourier transform? Yes, it is the Fourier transform of modulated SF. So e to the 2 pi I multiplied with f is giving a shift on the Fourier transform side. But modulation is a multiplication with a function which has constant value at every point. Therefore, it is not changing the L1 norm. And that's by definition the Fourier algebra norm of f hat, so it's translation invariant. Now, maybe I leave out the technical details of this argument, but in order to show continuity or so, we are again resorting to functions which have compact support. So what we have to observe is, if you're asking me, well, we'll look at the Fourier transform. We are asking what is a character with frequency Sn if you have a nearby frequency S0. So just imagine two functions, both of them having very similar frequencies. Then, of course, the difference of this globally, the uniform error, will still be 2. Why? Because if they're not completely exactly in phase, at some point one will be +1 and the other -1, and therefore the difference will be 2. However, if you're allowed to concentrate, that's the point here, if you're allowed to concentrate on X in some limited ball, then you can achieve that the difference, now, of course, what you are doing here, maybe I should have also spelled it out, you use the exponential law. The difference between two exponentials is by pulling out the chi of S0, so it's chi of S0 multiplied with the difference of the characters to 1. So this is pulling out chi of S0, but it's absolute value 1, so it doesn't show up. So you have to make that smaller than 1 for every x, which is more like this. Now, we have to recall that we are looking now at expressions of the form exponential function applied to a scalar product, where one of the partners is getting small. Now, we know that the exponential function is a continuous function. So if this is a complex number which is very small, so if y, or the absolute value of I times y, is less than some number, we are fine. Now, we use Cauchy-Schwarz to estimate the scalar product of Sn minus S0 times this x. So it's the ordinary Cauchy-Schwarz inequality, the Euclidean length of this vector times this. So you always can estimate this exponent. I think I should write 2 pi times y by this with the 2 pi, but the point is, if we make Sn minus S0 less than delta, then this whole expression will be so small that we can safely say that this is an exponential function with an argument, with a tiny argument, independent which s you use, because it cannot be larger than r. Therefore, this scalar product, which actually inserts, let's say, 2 pi times this, is at least delta times r times 2 pi, and that's approaching 0. So in the limit is 1. So therefore, you can have this. So this means that, and we are doing this standard approximation trick, we have to estimate something in the L1, or transferring the ms from the time side to the frequency side. It's a modulation. But if you assume it has compact support and by approximation we can do it, we only have to do it for k in this support. So again, if you want to show that you have continuous shift, the first is to approximate the f that you are using by compactly supported k, and I don't know, you use some epsilon over 3 to do that error, because you need it twice, once to go from MSF to MSK, then you go from MSK to K, and then you go back from K to F. But I'm leaving out these details. The point is, for compactly supported, the difference between is exactly this, but only on the support of K. That's the main trick here. So again, by approximation, or you get it for the full Fourier algebra. So we have this property, and I would like to mention this property. We have seen that the triangular function is in the Fourier algebra, so clearly it allows you to build partitions of unity, and we have just established that bounded measures act on the Fourier algebra, so this is no problem. Okay, so how are we going to use it? We're introducing a new space, or from each such homogeneous Banach algebra, we are introducing a new space. And I would like to remind you, my purpose was originally to say, we take C0 itself. For the bounded measures, we have this very nice and important property that splitting a measure into its pieces mu psi I. Taking the sum of the pieces is the same as the norm. So in measure theory, you have sigma additivity, and for bounded measures, you can split every measure into an absolutely convergent sum of the pieces. Now, clearly, this cannot be done for C0, because even if you take a huge plateau function, let's say from 0 to 100, you might need like 110 triangular function to represent it. And then that sum, the sum of the pieces in the supernorm, each piece would have size 1, would be 100. So it's clear that not every function can be controlled in this way. But in any such algebra, you can take every element, you can multiply it. The psi k is in the algebra, so it's meaningful to determine this, and you can ask this. Now, if you think again of the triangular function, then you observe immediately that this space is not the empty space, because every function which has compact support, so if it's living in a finite cube or so, or in a ball of radius r, will hit only finitely many such elements. So every element with compact support is in this space, and we have assumed that they are dense. So I'm creating a dense subspace, but with the extra help that we can play around with pieces. And we have seen already how convolution is well compatible with these pieces. So this is. Now, in going for a proof, and that's kind of a new proof, which is not exactly, very similar arguments have been used over and over for concrete or abstract situations like this. But I was trying to do a new direct argument. So I wanted to show a list of properties of these spaces, and for establishing this list, I was first establishing an argument which describes this space in a different way. So it's here I would say we take all the elements in A which have an absolutely convergent representation as the sum f equals the sum of f psi k, where the sum is, of course, convergent in the norm of A because it's an absolutely convergent sum, but it's also convergent in the pointwise and the uniform sense. So there's no discussion about how it's convergent. It's enough, but it's a very strong side condition. Now, the argument that we are using for the proof is the following. A function belongs to this space if and only if there exists some radius, I call it R, such that the function inside of A can be written as an absolutely convergent sum of the form HK. An absolutely convergent sum, of course, means that the sum of the A norms of the HK is finite. Maybe I should add this in the description. But each of them is living in some box, in some ball around some center. You can choose the center, but the diameter is at most 2r. So we are finding centers for, and actually it should be a support of HK, should be in some ball around some point labeled XK. So maybe right away, the first point is, if you see this decomposition, we are using a partition of unity, which is having uniform size. That's why it's called a BUPU, a bounded uniform partition of unity. So it's equal size or equal control of the size. So the elements described here are specific decompositions. So it's quite clear that the definition gives you elements which have such a representation. I think that's the first paragraph which I leave out. So the hard part is, if somebody is just coming randomly putting atoms, which are elements HK with this side condition, and we get them, then you can control them in a good way. So I call this an atomic characterization or atomic decompositions. And what are the possible atoms? These are elements in the space in the algebra A, which have a fixed radius in their support. Now, the argument is reduced to the fact that we only have to estimate the WAL1 norm, because if you're able to do this, then of course absolutely convergent sums of these things are also okay. Okay, so how do we do it? And it's a little bit similar to one thing that we have done already when we did convolution. We're interested to say, well, you're giving me an atom and it's living in some ball at some point. What can we say about this? And well, we know that there's a small radius r, typically, I don't know, little r equals 2 or so for triangular functions, or so, maybe larger, slightly larger for B-splines or so, but it's a fixed radius. They all have common radius, and they are centered at the points k. That's for simplicity. You can take a more general lattice. Now, the question is, how many k's are hit by this? So essentially you're saying, well, it's okay, these atoms have size 10, so we are living in a ball in R3 with a radius 10. Well, there are quite a few psi k's involved or so. We have to decompose the atoms into building blocks or so. Now, the argument that I would like to do is actually a visual argument instead of the details of this, because it's really a very simple argument. I have to do some correction, and it's this picture. So, yeah. So we assume that the centers of the red dots are the lattice points of the unit lattice. So these are pairs. Maybe in the middle you have 0, 0, 1, 0, 2, 0, 1, 1, and so on. These are the midpoints. Now, if we take the unit lattice, you can take circles of radius 1/2. They will touch, maybe open circles of radius 1/2. They will touch each other, but they will not at all overlap or so. And so the question is, well, you're using the functions psi, which are living around these red centers. Now, I would say that the problem is that by saying where are the psi i's, they're living in slightly larger balls. But if I would plot these larger balls, they would overlap and you would just cover everything. So the point is that I'm saying, well, the capital R is the yellow ball, so the yellow circle. You're interested how many red points have the property that they are touching the yellow surface or so. And the answer is, well, what you have to do is to make a slightly larger ball. You increase the ball, and then you're counting how many red balls or circles you can fit into the small ones. Now, because we have made the inner radius small enough so that they're disjoint, we're just saying, well, the total area of all the red objects must be at most the area of the blue object. So this is the whole game of the story. So how do we do it in a more direct way? We're saying, well, we have two balls. Think of this as being the yellow ball and this being one of the red balls. Maybe a slightly enlarged version of the red ball. Two balls intersect. They have non-trivial intersection if and only if you enlarge this from the center, and if you enlarge the center of the midpoint, so the yellow is enlarged to the blue object, but you take a radius of the form capital R plus little r. So if you're saying transfer the picture into a counting argument, this is the cardinality. So how many lattice points, how many red points can we have k, such that k is completely inside the enlarged radius that's inside this of any of the balls of this radius or so. And then you go by the volume. And the point is, I mean, I was showing you a picture here, but now you have to move the yellow object around. Maybe it's not aligned completely or so, but that will not change the argument. It's always only those red points which are kind of around or near the inside of the yellow one. They will be always completely inside and always disjoint inside an enlarged blue object, and that's what we have here. So it's a volume argument. The volume of this new one, and I was doing it exactly in the writing, it's enlarge the yellow radius capital R to the radius of the small object, and it's kind of red. R is the red one, which is disjoint, and +1 is to have the margins where the psi g's are living. So we have a fixed number, and that's decisive. So when you're asking, well, how can I estimate the AL1 norm, you have to compose any such atom which may live on the yellow domain. It has an A norm into pieces which are more or less around the red objects. And then you have to count how many are you using. And now, of course, what you also have here is, yeah, maybe you're saying, well, what is you give me one atom, number 7 or so, and then I'm saying, okay, I have to measure it. I have to localize it. So I kind of localize it to the red points. And then I have a product, but I can throw away, I can ignore all the pieces which are trivial. Kind of, if you're asking me an atom which is living here, far outside of the blue region, it will be 0. And so each time you're getting something, the part is at most, we have an algebra, the size of the psi j, but they're of equal size, therefore it's just the size of psi times the hk. So we have all of the WAL1 norm of h, actually I should say hk here, is at most the sum, oh no, sorry. Yeah, I should write maybe one line more. So this norm is at most the A norm of this. Now, if you have an absolutely convergent sum of atoms, you're giving me countably many atoms, H1, H2, H3, each of them being in A and having this norm. But if I convert these A norms to the AL1 norms, I will get this. So we have an estimate of this form, so we can split it. Now, I had first a proof, separate proof, showing that the definition should not depend on the partition of unity. Of course, you would say, I take the triangular function, another person takes trapezoidal function, anything like that would be okay. There are many, many poo-poos, but what we can easily see by the first part of the argument, each poo-poo with a certain size is creating atomic decompositions of a certain size. Therefore, you can control it with your fixed poo-poo. And so because you can do it in both ways, you can estimate it. And it's a definition which does not depend on the partition of unity. You can choose your favorite partition of unity. We also can say that there is a natural norm based on the atomic decompositions. So if you take all these absolutely convergent representations, you have a kind of a cost of getting this. So for me, this is like saying, well, what is the value of a basket full of goods that you get from a shop? Then you could say, well, I can buy it at this one shop, number 1, 2, 3, 4, 5. And then you would say, what is the total price in each of those shops? So each representation is kind of a realization of my order, and that would be the price of an individual order. But if you have 5 prices because you get the same basket from 5 different shops, you would say the value, of course, is the cheapest of all these. You're not giving it a higher value compared to what the cheapest is offering you. Now here we have not just 5 different representations, but uncountably many, a huge amount of different representation. You can have stupid representations with a building block added 3 times and subtracted twice instead of just using it once. So there's a huge variety, but There are good ones which are kind of saving total cost, which is the total sum. And there's an infimum, and that can be, I mean, it's clearly cannot be arbitrarily small. So you can call this the value or the actual size in the spirit of the value compared to the cost of a representation. So every admissible atomic representation which for a given radius is allowed here, and the infimum for a fixed radius is giving you this. Of course, you can ask, well, what if I change the radius? Well, if you allow larger radius, you get more representations, so they will become cheaper. But if somebody says, no, I want to reduce the radius, then of course you have to split your big baskets into smaller baskets, which has a certain price. You get a new constant. But again, of course, it has to be independent, because if every such representation for fixed radius is equivalent to a Bupu, which is also fixed, then mutually you can go from one Bupu to another and change the radius in the atomic representation, and so on and so on. So now, having said this, I would say let's take this fixed Bupu for the discussion, maybe triangular function for the Fourier algebra or trapezoidal function for the Fourier algebra is a good example, and let's try to get the list of properties. So we are already very close to the properties of S0, which will be the key object of our discussion. So the first thing is, well, this is really a decent norm, actually, one of the natural norms of the space, and it's a Banach space. So it's very easy to see that it's satisfying the triangular function, triangular inequality, and you have to work a little bit for the completeness. We get that the elements which have finite partial sums are dense, which are exactly the compactly supported elements. The translation operators are uniformly bounded, and that's actually a place where this atomic decomposition is more convenient, whereas for a fixed partition, it's a problem. I'm sorry, I didn't look at the chat. Yeah, I will take care of this. It was about the definition of the atomic representation. So it's also a Banach algebra with respect to pointwise multiplication, but it's also, I didn't write it here, it's inside L1. So if you see, we will see it's also closed under convolution, which is the next statement. And you can do dilation either in the ordinary dilation sense or in the compression sense. Now, I think it's a little bit boring to go through all the technical steps. I tried to write it down in a careful way. But for example, the completeness may be considered rather complicated stuff if you take, for example, the atomic representation, because then you have countably many sequence of elements. Each of them has a countable representation and so on. I think here the Bupu stuff is much easier. So if somebody is giving you something which is absolutely convergent in this new space, WA-L1, I say it's the Wiener amalgam space with local component A and global summability L1. That's just the absolute sum of the terms. So what does it mean that I have elements Hn? Because I want to split them into pieces, I write this script, the label of H1, H2, H3 in the on the upper side. So it's not a power, but it's just a label number n. It should be actually from n from 1 to infinity, not from minus infinity. Then we can control this. By this, we can control the A norm. So it's also absolutely convergent in A. So it will be some element. This series is nicely convergent, so same summation in A. Now, if it's convergent in A and A is inside of C0, it will be convergent, uniformly convergent, pointwise convergence. So it's a decent, nice, continuous function in C0. We can localize it with psi k. And of course, if you sum a function, many functions, and then you localize it, you can equally, because it's pointwise conversion, you can do the same thing by taking each function h and localize it first, and then sum up over all these pieces for fixed k. But all these pieces are in A, they are absolutely convergent, and therefore you get that the h psi k is controlled by the sum of the pieces, but by the definition, this double sum is finite. And maybe here the completeness comes in. When you have a double sum, you can change the order. You can either sum over the k or over the n first. Actually, it's a bit nonsense here. The k should be actually over the integer lattice, so k should be in set d even in the multidimensional situation, whereas n should go from 1 to infinity. So clearly I have to correct it. But you get completeness. Now I think I can skip many other details or so. Maybe I'm trying to show you the relevance of the pieces. And that's maybe for now the end of today's session. I will show you that bounded measures act by convolution on the algebra. So we assume first that MB with A is okay, but then we have to control it. And we're doing very much the same game as we did when we were showing that bounded measures with C0 are going to 0. We decompose the measure into pieces, and here we get absolute convergence for free, and here we are getting in by definition. So what we have to do is we split it to a double sum, and we know already now that we can reduce everything to compactly supported elements. So we are fine if we are doing a correct estimate with constants not depending on how big our finite sets F and E are. We can take M psi I with I in the finite set F, and F with psi j, the same or a different bupu, with a finite set E. Now, if you have such a double sum, the trick is, now you can say, well, it's pairs, but it's finitely many pairs. So let's relabel them. Let's say these are atoms L, and it goes from the first to the last, and I should write H sub L. I've changed it too much in the writing up. Is one of these elements. And so what I have to, what I can use is that the HL is dominated in the A norm. But now the point comes, I'm referring to the atomic decomposition. Where are they concentrated? Well, the measure is concentrated around the point I. This is concentrated around the point J. So maybe this is living in the interval from 3 to 5, centered around 4. This is in the interval from 9 to 11, centered around 10. So the center are added, which is 4 plus 10 is 14. But of course, you take a larger interval, so it's from 14 minus 2 is 12 to 14 plus 2 is 16. So that's essentially the main point. And this was already because we were seeing this, that you're writing the convolution product, and whenever the shift parameters are too far apart from the possible center, you get nothing. So what we get is, we get a control on the norm. So this is an atom, and it has a size of the support, which is only depending on the size of our bupu, and so it's a fixed radius or so. And because we have this, we get an atomic representation, and therefore we are controlling, as we expect, the AL1 norm of this. So this is kind of, again, coming back to this idea of reducing everything to pieces, doing it for finite sums, and the rest is approximation going to infinite sums, and these infinite sums are dense in the full space. Therefore, we have this very important property that bounded measures multiplied with AL1 are this. And just as a preview on where I will start next, we will see that the particular choices is C0L1, which is known as Wiener's algebra, and FL1, which we have studied a little bit so far already, will give you the Siegel algebra as 0, which I have depicted as this small round magenta object in my zoo of function spaces. But this will be discussed and will be in the center of the more or less the rest of the course, and that's where I stop for today.